thank you again, Dr. Sarangi. So as you can, by now you know that I am Neeraj Kasturi and I am working in Geosciences Division of Physical Research Laboratory. It is commonly called as PRL Ahmedabad. It is under National Labs of India. Research, if you talk about from the core of the Earth up to end of universe, that is the domain of research at PRL. And I work particularly in atmospheric sciences. And in this lecture, I will be mainly talking about, I will go exactly like the title what you see, organic carbon, brown carbon, and insights from real-time measurement. So first means what does that mean? And so if they are there, they are there. How does it matter? So what we get, what information we get if we are measuring them. So in case if you are not able to ask any question, if you want to ask me further, my email ID is given at the bottom. You can write me anytime you want. And okay, so let us start. So let me start with carbonaceous aerosol. We all know about this. And one more thing is, I have seen the schedule and I noticed that people have already told you about why aerosols are important and what are aerosol, basic properties. So I am not going any of those things. I am directly jumping to the organic aerosol. Okay. So carbonaceous aerosols are composed of black carbon and organic carbon. Black carbon are well-known primary particles. Primary means the particles are coming as a particle in the atmosphere and they are well-known absorber. They absorb light. Organic carbon, on the other hand, they can be primary or secondary. Primary means it is coming as a particle. Secondary means they are forming in the atmosphere. And they were known as scatterer until recently. But then these people, Henry and Gerenser in 2006, they have said no, there is a fraction of organic carbon which can be absorbing, and that is known as brown carbon. And this brown carbon can also be primary or secondary. So here we see the classification. So what we see here, that this is chemical refractiveness and this is optical absorption. So what they propose that, okay, organic carbon are non-refractory, elemental carbon are highly refractory. Refractory means stable at very high temperature. So 800, 900 degrees centigrade if you are heating, then also they are stable. Which are not stable, they are called non-refractory. And there is something in between which is refractory organic carbon. Optically, this is elemental carbon, this is black, and organic carbon is white or colorless. And in between whatever is there, that is called colored organic carbon. That is what they proposed as brown carbon. Chemically, if you talk about, they propose that low molecular mass hydrocarbons and their derivatives are this organic carbon. Graphene layers of carbon, that is elemental or black carbon, and then polycyclic aromatic or humic-like substance or biopolymer, these kind of compounds, they are colored organic carbon. But that was the understanding that time. Now you will see that there are brown carbon which are non-refractory, which are highly volatile also. You will see as the talk will progress, you will see about those things. So means organic carbon can be absorbing even if it is non-refractory, and that is brown carbon. So unlike black carbon, which absorb throughout the wavelength, if you see it is absorbing from 300 to almost 800 nanometer, brown carbon absorb in near UV and visible region. This is the range given here, and maximum it absorbs near UV. Okay. So how does it matter? Means whether is it brown carbon is more absorbing than black carbon? No. Black carbon at any given time is the most absorbing species. After CO2, this is the second most absorbing species in the atmosphere. But if you talk about organic carbon, the mass fraction of organic carbon is much higher than black carbon, means 2 to 20 times higher, whatever is reported over India. So what does that mean? That light absorption by brown carbon could be significant, and that should also be considered while assessing the relative effect of carbonaceous aerosols. Okay. Now let us talk about what is organic aerosol. So in our 10th, 12th, we studied that there are alkanes, there are alkenes, alkynes, and then we know that there are aromatic hydrocarbons with benzene ring. Then what else we know? We know that aliphatic hydrocarbon can have functional group also. Then you will call it alcohol, aldehyde, ketone, carbonate, carboxylate, etc., etc. Many things you can call depending upon what functional group you are adding to that. Then aromatic hydrocarbon can also have this functional group like toluene, phenol, aniline, benzaldehyde, benzoic acid, etc., etc. Then you can have polycyclic aromatic hydrocarbons like naphthalene, pyrene, chlorine, pyrene, acetylene, naphthalene, etc., etc. Why I am showing all these chemical structures? I don't want to scare you. I am just telling you that organic aerosols can be composed of thousands of species with different physical chemical property. When we talk about, say, inorganic, so you will say there is sulfate, there is nitrate, chloride. If you go a little further, you will say ammonium, sodium, potassium, calcium, magnesium, and some metals. So there are limited number of inorganics. But when you talk about organics, there can be thousands and thousands of species with variety of chemical and physical properties. So it is complicated. So let us move further. So what are the sources of organic aerosol in the atmosphere? So it can be primary. As I said, primary means it is coming as a particle. So primary, mainly it comes from biological aerosol particle. So it is called PBAP, primary biological aerosol particle. And how it is coming? It can come from plant debris, it can come from pollen or bacteria or viruses, fungus, algae, etc. etc. There are studies who estimated that PBAP may be as large source as dust or sea salt. That means about thousands of teragram per year. Other studies said that emission of fungal spores alone can be about 50 teragram per year. So that means amount of organic aerosol is huge in the atmosphere. Then let us talk about secondary organic aerosol. So I am sure that you have this lecture on VOC. VOC is volatile organic carbon, which comes from biogenic and anthropogenic sources. Majority of the VOC come from biogenic source, about 80%, about 20% come from anthropogenic emission. Biogenic VOCs like isoprene, anthropogenic like BTEX, that benzene, toluene, xylene, etc. All those VOCs, when they come in the atmosphere, then they react with oxidants. These oxidants are ozone, hydroxyl radicals, nitrate radicals and all. After reaction, they form secondary organic compounds having broad range of volatilities. And ultimately, if they are in the atmosphere, they will keep oxidizing, and ultimately they will convert into CO2 if they are going in gas phase alone. But there can be partitioning into particulate phase via different processes which are listed here, like heterogeneous reaction. Heterogeneous means you are talking about different phase involvement. So gas versus solid, gas versus liquid and all. There can be photolysis, there can be condensation, evaporation, there can be aqueous phase reactions. So once it partition, it comes to particulate phase, right hand side. Then there can be oligomerization. What is oligomerization? We all read about polymerization. A small scale polymerization is called oligomerization. And these compounds can be semi or non-volatile organic compound, and then they will behave like aerosol, like other aerosol, and they will get removed from the atmosphere by wet and dry deposition. If we talk about the SOA budget, there is a large uncertainty ranging from 25 to 200 teragram per year, as reported by these studies. You see, the mass of secondary organic aerosol is much less than what we have seen in the previous slide from primary organic aerosol, but both have different importance. Now, primary or secondary, once it is in the atmosphere, then another headache. It is dynamical, means it changes dynamically. How? During atmospheric aging, I hope somebody would have told you about aging. Aging means when aerosols come into atmosphere, that means they are born, and then they move along with the air, and they keep moving, and finally they get removed from the atmosphere in about a week or so. But the time what they spend in the atmosphere, they undergo variety of chemical changes, physical changes, optical changes, and that is called atmospheric aging of these aerosols. So for example, this is one organic compound is shown here. What can happen? It can go under oligomerization, which I explained you in the previous slide. There can be functionalization. That means this was the organic compound, and then one H is replaced by OH. So that means you are increasing the mass of this organic compound. The volatility will decrease. O by C, O to C ratio will increase. There can be fragmentation of this compound somewhere in between, and then you have different compounds. Then mass will reduce, volatility will increase, composition may change, and it depends upon where bond breaks and what gaps end. So overall, organic aerosol composition is dynamic and a big headache for modeling. Then the question comes, how do we study organic aerosol? What is the way? So now let me show you some ways. Before I go to that, let me show you this diagram which was reported by Hallquist in 2009, and he has very nicely summarized this. See, on x-axis it is chemical resolution. That means one type of organic compound, few classes of organic compound, many classes, or molecular ID. That means each and every compound you know that whether it is benzene or some particular pH or some dicarboxylic acid, what is that? That if you know, that is molecular ID. And then completeness, that means out of total, how much you are able to measure. That means are you able to measure 100% or just 10, 20, 30, 40%. And what we see here, that if we have any instrument which lies here, that means it measures only one class, or which green sums, we are looking something green and some 5-10%. So that means it is useless instrument. Perfect instrument is you are doing 100% you are telling, and for each compound you are telling that what is the molecular ID of that compound. So that is perfect instrument, which is not yet existing. I hope it will come with time, but not yet existing. So what are the existing instruments? We have ECOC analyzer. It will give you 100%, that how much organic, how much black carbon is there, but it will just tell it is organic or black carbon, that's it, nothing more than that. Then you have some other instrument like PILS, WSOC, I will talk about this. PILS is particle into liquid sample, and WSOC means water soluble organic carbon. And then NMR, FTIR, AMS. So here you see the mass, percentage of mass is increasing, but it is able to tell only few class of compound of organics. Then you have GCMS, which will actually give you molecular ID, but percentage wise just it will tell you 10-15% maximum, that how much is these particular compounds are there. As I said, perfect instrument is yet to come. Now let us little bit talk about the offline measurement of organics. So as Dr. Sarangi was indicating that you have been already told that how people collect aerosol and all. Let me just add little bit to it. So you take high volume sampler or low volume sampler depending upon your requirement, and then you go wherever you want. You want to go to mountains, or you want to go to some urban area, rural area, you take ship and go to ocean, or you take balloon, go up, wherever you want to go, depending upon what your objectives are. You take the sampler, you collect the filter and bring it back to the lab. Now you have a sample. Then means just showing you an example. Before sampling, this is the filter, it look like, and this is typical urban aerosol. Means after about 12 hours of sampling, you see this kind of layer of aerosol. This is what we have collected, sample filter. And then once we have filter, we use variety of instrument. For example, I was showing this OC-EC analyzer I was showing in the previous slide. It will give you OC and EC concentration. Then you have TOC analyzer, it will give you some other species and GCMS. So what we measure OC-EC by this. BrC is brown carbon, which I will be telling a little later. WSOC and WSON. WSOC is water soluble organic carbon, water soluble organic nitrogen. That is measured by this QCT analyzer. And then this diacids, dicarboxylic acid or pHs or sugars and all, that can be measured with GCMS. So you take the aliquots of filter and analyze different component in that filter. So that is how you get. Then another question comes, what is the need of doing all these things? So what you will get, suppose if you measure the diacids or pHs or sugar, so what? Okay, whatever is there. How does it matter? Why do you want to know all these things? So let me tell what we learn from these things. So first I will tell about what you learn if you have OC, BrC, WSOC and WSON measurements. So that is like broader characterization of organic aerosol. Right? Let us try to understand it. So if we are measuring OC and OC by EC ratio, what do we learn from that? So first thing is, and now I have listed many studies here, and one more thing let me just tell, that whatever studies I am going to write here or show, I tried my best to use Indian studies only. So I am showing Indian studies only. So these are the studies, and over India I am talking about mainly, wherever possible. So organic aerosols are significant or dominant fraction of ambient PM over different Indian range. What is the range? Is 25 to 80%. Now you notice means OM and OC both are different things. When we talk about aerosol, you have OM or organic aerosol in there. But what we measure is organic carbon. Carbon and means organic carbon or organic mass. What is the difference? For example, suppose if you have glucose compound is there. So if we take the OM by OC ratio, if you take the whole molecular weight, it is about 180. But if you see only carbon, which is 6 carbon, so that means 72. So if you take the ratio, it is 2.5. That means OM by OC ratio, if you have all glucose, it will be 2.5. If it is all like benzopyrene kind of compound, then it will be about 1.06. But in the atmosphere, neither you will have only glucose or nor you will have only benzopyrene. It will be mixture of many compounds. So what is the typical ratio people use to convert OC into OM is 1.6 to 2.2. 1.6 is used typically for urban aerosols and 2.2 is used for aged aerosol. If you are say, some mountain or some oceanic region where you have transported aerosol, there you use 2.2 ratio. Okay, moving further. So what OC by EC ratio tell you? So I am talking about broad composition right now. So now you have measured OC by EC ratio. That will tell you the relative dominance of biomass burning versus fossil fuel burning. Lower ratio, if it is if you in your sample, if you have measured the ratio less than 1 or 2, then you will say it is fossil fuel dominant. FFB is fossil fuel dominant. Higher the ratio, more than 2, higher the ratio, is more the contribution from biomass burning, or there can be more of secondary organics as well. Why means if SOA is there, then OC by EC ratio will be high? Because when we talk about secondary organic aerosol, there is no secondary black carbon. Black carbon is always primary only. So if secondary organic aerosols are formed, there is no EC coming from that source. So that will keep increasing numerator. So that ratio will increase. So there you cannot say whether it is from biomass or fossil fuel burning. But otherwise, in a broader way you can say higher ratio means biomass burning, lower ratio means fossil fuel burning is dominant for carbon aerosol for that site in that season. Okay. Then what else we measure? We measure WSOC, and which is considered as a measure of aqueous SOA. With higher the WSOC by OC ratio, see WSOC is a part of OC. So how much it can be maximum? It can be 1, means the ratio can be 1. That means all organic carbon is water soluble, or there is no water soluble, means all is insoluble. So the ratio can vary from 0 to 1 WSOC by OC ratio. But higher the ratio means more the contribution from secondary organic aerosol. And over Indian region, if you see, the people have reported from 0.2 to 0.95 WSOC by OC ratio, which suggests the variability in SOA fraction over different regions. And then people also measure WSON. What is that? Water soluble organic nitrogen. So that is important when we talk about nitrogen bucket. Mainly, in aerosol it is mainly ammonium and nitrate, the nitrogen form, but there can be significant organic nitrogen also. And people have reported about 10 to 30% of WSON by WSOC ratio, where this 10% is over urban region, and if you go to marine region, then it is up to 30%. Okay, let us move further. So what will you get if we have now analysis of organics at compound level? So this was first done by this Shower and Cast in 2000. This Shower, if you know, this is J.B. Shower, is the chief editor of Atmospheric Environment. Anyway, so what they have shown that this is the concentration they have measured. So see, 0 to 20 microgram per meter cube. But what they were able to analyze was only this. That means up to 2 microgram. This is almost 10%. So they could resolve only 10% of organic aerosol, and what they found, there were alkanes, fatty acids, substitute phenols, levoglucosan, sugar derivative, and other compounds. But again, question comes: suppose if you know all these things, so what do you know? Means what do you learn from that? So let us try to understand a little bit of that also. So suppose we measure sugars. Now this figure I have taken from this Tang et al. And this is the measurement of sugars in organic aerosol. So what are these sugars? Levoglucosan, galactosan, mannose, erythritol, mannitol, etc., etc., glucose, fructose, etc. And this is mean, this is daytime, nighttime, that you can see. But total contribution, if you see, total sugar contribution to total organic carbon is less than 1%. Mass wise is not contributing, but it is giving you some information, some important information. So for example, levoglucosan, which is produced by the pyrolysis of cellulose present in organic matter, and then mannose and galactose, they are also produced. So they are the unique marker of biomass burning derived aerosol. Earlier what I was saying, that OC by EC ratio is the crude way. But suppose you have high OC by EC ratio, but there is no levoglucosan, then you cannot say that it is from biomass burning. But if you have high OC by EC ratio and high levoglucosan also, that means you are sure that it is coming from biomass burning only. Okay. And then similarly, if you have erythritol or mannitol, then they are a tracer of airborne fungal spores. So that means by measuring these sugars, we can find out that whatever organic aerosol we are measuring over a given site, what are the sources of those organics, and then you can identify whether those sources are local or they are coming far from other places and all. Okay, now move further. So suppose if we are making dicarboxylic acid in organic aerosol. So this is a study by Deshmukh et al. Where they have measured many of the dicarboxylic acid and some other related compounds. Diacids are a fraction of WCC and recognized as a unique fingerprints to identify atmospheric process, which is photochemical formation or degradation. If there is a formation, you have more of these compounds. If there is degradation, then it will go towards left. And diacids are shown to contribute about 0.2 to 2% over urban region and about up to 16% over marine region. Let us move further. Now pHs. Suppose if you are measuring pHs. So why people measure pHs in organic aerosol? First thing is that pHs are well known carcinogens. Carcinogens means they can cause cancer. And if there are derivatives like oxy, chloro or nitro derivatives, then they are even more carcinogenic. In addition to that property, if we measure this different pHs, what we learn, see Prashant Rajput, he has reported a couple of papers. His whole PhD was from pHs. And what he reported that total contribution of pHs also was less than 1% to total organic carbon, but they carry the signature of origin. For example, biomass burning, fossil fuel burning. So what he used these different pHs, whatever you see on left and y and x axis. So nth is anthracene, phenylephrine, ICDP is indole, pyrene, benzoperylene, chlorantine, pyrene. So using the ratio of these pHs, you can identify whether pHs are coming from regular or coal combustion, or whether from paddy residue burning or wheat residue burning. So these kind of fine features you can find out if you are doing the molecular characterization of aerosol. Then let me just tell briefly, means I will not go in detail. This is one of my student is working on this particular topic right now. He is using 13C and 14C to characterize the carbonaceous aerosol. How? See, if you are making 14C we know it is radiocarbon, and we know it is the half-life of 5730 years half-life. And fossils are, means more than lakhs and millions year old things are there, that is fossil. So that means if carbon is coming from fossil, there will be no 14C. But if it is coming from biomass, then it is contemporary. Whatever 14C is there in the atmosphere right now, that similar 14C you expect in biomass. So by measuring the 14C in aerosol, one can quantify that how much is coming from fossil fuel and how much is coming from biomass. For example, if F-bio is the measure of 14C. If it is 0, that means everything is coming from fossil fuel only. If it is 1, that means everything is coming from biomass burning only. And if it is in between, then you can calculate that what fraction. For example, here, if it is 0.85, that means 85% is from biomass and 15% is from fossil fuel. So 14C is a unique tracer to quantify fossil fuel versus biomass. And then if we are doing with 13C, then it will also tell that not only source, how processes are changing the composition. For example, this is the figure I have taken from Prashant. So what it shows that F-bio versus 13C for the samples collected during from Patiala during paddy residue burning, and then pre-burning, post-burning, all these things you can see here. So what we infer from this, that 13C in 14C aerosol from paddy residue burning or Patiala revealed night-time samples during intense paddy residue burning, PRB is paddy residue burning, lie outside reported UV range. So this is the reported UV range. But if we take it further and intercept, so the intercept will become coming here. So that means 13C is actually minus 29 compared to whatever is reported here. And what else? Now see, 0.85. For example, all these samples, F-bio is 0.85, but 13C is ranging from here to here. So what does that mean? That means it will reflect the process. So I was showing when secondary organic aerosol, I think I was showing that there can be partitioning, there can be aqueous formation, there can be photolysis. So all those processes we can try to understand if we are doing both 13C and 14C in organic aerosol. Okay. So what else? Now let me tell a little bit about the brown carbon. So brown carbon, as I told in the beginning itself, that it is a fraction of organic carbon. Okay. Now how much fraction is that we don't know. And how do we measure? That is measured optically. How? So first we extract the filter. Filter you know how to collect. You extract the filter with some solvent. The solvent can be water or it can be methanol. And then you measure the absorbance of that extract. Then this absorbance you can measure at a certain wavelength, or you can measure the whole spectra, whatever spectra we were talking about that time. And then you calculate the absorption coefficient, which is at V abs lambda is at a given wavelength. So this is how you show brown carbon. So for example, 365 is the most commonly used wavelength because Hewlett, that is the most stable brown carbon, that absorbs at 365. So that is why this is the most commonly used V absorbance at 365 is the most common general measure of brown carbon. But if you are measuring the whole spectra, for example, absorption factor of BrC, it depends upon both composition and concentration of BrC. So when we are measuring in extract, there is whatever BrCs are there, all are there. And some BrC absorb at some wavelength, some other are absorbing at other wavelength. But what we are measuring is all sum of all the BrC spectra, right? So by looking, I will tell you what we can do here. So here at different type of BrC absorb at different wavelengths. For example, Hewlett type of compound are there, they absorb usually at less than 400 nanometer. And if there are nitrogenous organics and some other secondary BrC, they absorb at wavelength higher than 400 nanometer. How we can utilize that, we will be talking shortly. Once we have this absorption coefficient, then we calculate mass absorption efficiency, that is MAE. And remember, here this is how we calculate. Here we are using WSOC, not BrC, because we are not measuring BrC, right? We are measuring just absorption coefficient and WSOC, which is actually measured. So whatever you are getting, that is the lower limit of BrC. Whatever MAE you are getting, that is the lower limit of BrC, because this ratio BrC to WSOC is somewhere from 0 to 1. What it means? That means whole WSOC can be BrC, or there can be no BrC WSOC. So overall, what we should remember that if you have higher MAE, that means either you have larger fraction of BrC WSOC or more absorbing type of BrC present in WSOC. And if MAE is lower, that means BrC is either not there or very less absorbing BrC is there. Means just by looking at the number of MAE, you can talk about how much BrC is there or not. Okay. So how we use that? So this is a typical spectra of BrC you get. So this is wavelength and this is absorption coefficient as a function of wavelength. And whatever I have shown here is average BrC spectra for daytime means blue and night time is red. And these samples were collected during petty residue burning over Patiala. And we proposed something. We proposed a simple and novel approach how to assess the composition and characteristics just using the spectra of BrC. So what we propose, before that let us understand. So if it is changing on y-axis, so that will show you the concentration change in the variability in BrC concentration. Higher the BrC concentration, you have more absorbance, more absorption coefficient. And if you have variability in this x-axis, that will tell you the variability in BrC composition. That means earlier different type of BrC was there and now there are different type of BrC. But how do you know that? So what we propose that if BrC composition is uniform, composition means same type of BrCs are there, then what we expect that if you divide nighttime spectra by daytime spectra, there should be a flat line. And flat line, this should be constant. This constant can be 1, 1.5, 2, 3, whatever. And then that number will tell that, okay, nighttime concentration is 2 times or 2.5 times higher than daytime concentration. But if it is not uniform, see, on right axis I have shown the ratio, which is ranging from 1 to 3. And their ratios are different at different wavelength. So if it is not uniform, that means you have different type of BrCs at which are during night time compared to what you have during night time. For example, here you see this ratio is for around 370. Ratio is about 3. But if you see here at 550, ratio is about 1.8. So that means during night time, the BrC which are absorbing at this wavelength, they are about 1.8 times higher, whereas the BrCs which are absorbing at this wavelength, they are about 3 times higher. So, and how do you identify this thing? Just by looking at the spectra or using the spectra. And we have already understanding that if it is less than 400, then it is Hewlett's type of compound. That means biomass burning will be giving you large amount of biomass burning. And right hand side, it is more of secondary BRC. Okay. I saw someone has said that there is some sound problem. Are you not able to hear me?
Yeah, now it's clear. In between there was a little bit inconsistency. Now it's clear.
Okay, okay. Okay. Let me continue. Okay. So what overall means, there are not too many studies over from India, but what they have reported that BRC is composed of multiple species. That means Hewlett's type of compound, nitroorganics and all. They contribute significantly to total OC, and their optical properties are highly variable. Okay. Now let me move towards online studies. So whatever I was talking so far, that was all filter-based study. Now I will talk about online studies. So what is that? Pills-based study. Pills, I am not giving you any tablet. I am talking about pills, means particle into liquid sample. What is that? So that is an instrument which gives you water extract continuously. Water extract of ambient aerosol. That means it pulls the air from the ambience, and then if there is a system, it will leach the aerosol and it will give you the water extract. Now you filter it and then you can use it wherever you want. So what we did, we used it extract, whatever extract came, we used for acidic PEM and we pushed it to LWCC. So here we could measure brown carbon, and then the same extract we have forwarded towards QC another, and that gave us WSOC. What was the time resolution? It was 2 minutes. Every 2 minutes we were getting the data, and every 4 minutes we were getting for WSOC data. And then you have other things which are obvious. So what do we learn from this kind of studies? See, this is the study which was carried out over Kanpur, IIT Kanpur, and we measured online WSOC, online BRC, and first see this is scatter plot. This is WSOC, BRC, and we see overall slope is 1.22, but we see there is a large scatter. And if you notice the color, see these color, this yellow, green and red, they are afternoon hours, and this color either belongs to late night or late evening or very early morning. So what does that mean? See, we know that this slope is actually MAE, if you recall, B absorbance upon WSOC, that was the MAE. And I told you that higher the MAE means more the BRC component. So what we see that it is actually varying, see, from here to here, the slope is having large variability. If we see in terms of number, MAE of WSOC, which is given by the slope, was highly variable from almost 0 to 5.26 meters square per gram. What other information we got? Then we categorize this into different time zones. So that we have taken from there. So this is the diurnal trend of WSOC and diurnal trend of brown carbon. So we have categorized that into different parts. And MA during evening plus night hour, and in this plus this, it was 1.34. Morning hours, that means this, or 0.95, and middle of the day is 0.58. This. So that means during different time of the day, you are having different MA. That means optical property of brown carbon is highly variable. And how do we ascertain that? Means that was based on, we also ran in parallel AMS, which I will be talking about, and that data supported whatever I am saying. During morning hours, this WSOC by CO ratio, which is an indicator of SOA formation, that was high. So that confirmed that morning hours it was because of secondary of the aerosol formation, that whatever BRC you found. And middle of the day, the kind of MA you got, that suggests that ambient BRC goes through photo bleaching during daytime, or it is volatile and evaporate because the temperature is maximum during that time. So overall, it depends upon the type of chromophore, primary or secondary, or meteorological condition. So that decides about carbon property at a given time. Moving further, now same B absorbance at 365 and then we correlated with all different means. We measured optic aerosol with AMS, and then we did PMF analysis of that, and PMF analysis will give you different type of organic aerosol. For example, this HOA, etc. you can see here. So what you did is you did it for organic aerosol. PMF derived factors were like hydrocarbon-like organic aerosol. That means they are purely like hydrocarbons. Then low volatile oxygenated organic aerosol. Then biomass burning organic aerosol. Semi-volatile oxygenated organic aerosol. Biomass burning organic aerosol type 1 and type 2. So we correlated with all these PMF factors. And what we observed that the slope was highest for SVOA, BBOA2 and lowest was for LBOOA1, which tells you, if you see the different slope, the absorption, which simply tells you the absorption capacity of BrC from different sources. That means BrC coming from different sources will have different absorption properties. It will not be same for all the sources. And one was not included, this LBOOA2 type was not included because this pollution was very poor. And this category comes under highly oxidized or aged OA. So we infer that if organic aerosols are oxidized or aged, then their BrC component is almost zero. Moving further, now this is another unique measurement. Means this is unique. I am saying that nowhere else you will see this plot because it is not yet reported like this, the way I am showing you here. This was again pills, WSOC, LWCC, but earlier whatever I was showing was at 365 nanometer. But here what I am showing is, see, this is the diagonal trend of the whole spectra. So x-axis is obviously hours of the day, y-axis is wavelength, and the color is absorption coefficient. So that means at a given hour. So this is showing you that this is the spectra, means vertically whatever you are seeing, that is the spectra. And then how it is changing with time. And you can see the variability during the day. Means this is from Delhi, IIT Delhi, we have done the measurement recently. And what do we learn from this is that there are primary and secondary formation processes available. And then you have, okay, there are primary and secondary formation processes which are highly variable. And then you have various bands of absorption, likely due to the difference of different group of BrC species. See, band you can see this color, this color, this color, all these colors are different. And they were in different band, for example, 300 to 360, 360 to 390, 390 to 410, 410 to 440, 440 to 460, 460 to 530. So all these trends were different. For that means you have a variety of BrC species which are varying in a different way. And this understanding we already have that Helios type of compound absorbs at less than 400 and nitroorganics absorb at more than 400 nanometer. And minimum absorption, if you see, they were all observed during afternoon hours. So which could be effect of either, we know that afternoon hour, this planetary boundary layer, that expansion is there, so all the concentration goes down during that time. Or they can be photosensitive, or they can be volatile because temperature is also high during this time. And then if you see the MAE variability was much less than compared to this B absorbance variability. So what it means, either that WSOC and BrC both were varying in a similar manner, so that ratio means MAE remains similar. But overall, if you see, the nighttime MAE was higher than daytime MAE. That means nighttime brown carbon is more absorbing than what we get during daytime. And it also tells one thing, that if we are doing filter-based measurement, say if you are doing 24-hour average sampling, so you will see the effect of whole, means average of everything. Now if you are doing 8-hour sampling and you chose the 8 hours from afternoon, so you will get very low concentration. If you select during night time, you will get very high concentration. So that means it can be biased. So if different people at same place, they are observing at different time, they will say different results, which you can say only when you are doing this kind of online measurements. Okay. Now moving further, now let us talk about AMS based studies. AMS is high resolution time of flight aerosol mass spectrometer, and it talk about non-refractive organisms. You remember in the beginning I told you non-refractive means which are volatile at lower temperature. So this plot I am sure Sachin would have shown you. His paper was there in Nature Geoscience. Very limited studies are there. from AMS or ACSM. If you see, means sites are only 5. You see more pie chart, but sites are only 5 because, for example, this is our study. These two Ahmedabad, these are our studies, but means from the same site. So that means very less study. This organic aerosol with AMS is very understudied over India. But what do we learn from this? So what we have seen that most of the studies over India reported that OA is composed of HOA, POA, PBOA, SPOA and LBOA, and these are the studies, most of the studies which are reported so far on this using AMS and ACSM data. Okay, so what we learn from that, let me go now, what science we learn from that, let me go into that. This is for sources. So based on, by doing PMF of OA from AMS, you can get some idea of sources that, okay, whether it is BBOA or HOA or POA and all. But what other thing, what process you learn from this? So let us try to understand that also. So this figure I have taken from Kroll et al. And what we see here is number of carbon atoms on x-axis and oxidation state of carbon on y-axis. And we know that carbon oxidation state vary from -4 to +4. -4 is for methane and +4 is CO2. And all other things are in between somewhere. So what Kroll has suggested that if this oxidation state, when coupled with number of carbon, it provides a framework for describing the chemistry of organic species in the atmosphere. What does that mean? So see, if you have any compound at any place, if there is a fragmentation, it will go like this. That means fragmentation is number of carbon will decrease, so it will go in the right hand side on this chart. But at the same time, it will, if it is oxidizing, then oxidation state will increase. If there is a functionalization, then it will go up. Functionalization means you are increasing the oxidation state, so it will move towards up. If there is a oligomerization, I told you oligomerization means small scale polymerization. So number of carbon earlier was less, but after oligomerization it will go towards left. So if it is oligomerization, it will go like this. So that means by looking at the oxidation state and number of carbon, one can understand that whether organic aerosols are going which process, fragmentation, functionalization, oligomerization, etc. Okay. Now what else we can learn? So one more thing, if you are using AMS, high resolution AMS, it gives you H by C and O by C ratio. And this is the Venn Cleveland diagram. So what do we learn from here? See, if you remove from existing organic carbon, if you remove one H and add OH, that means alcohol, then the slope will remain 0 because you are removing, adding one O, but you are keeping the H same. But if you remove 2O, 2H, that means if you are replacing it with carboxylic acid, then slope will be -1. And if you replace CS2 with a carbonyl group, like this group, then you are adding one oxygen and losing 2 hydrogen. Then slope will be -2. That means if you are just looking, you just plot H by C and O by C on Y and X axis and throw all the data point on this. Then depending upon where these data points are lying, you can talk about that what compounds are there in these aerosols. And this is very interesting. Surprisingly, despite complexity, changes in aerosol composition during aging, overall it looks like that everything is going towards carboxylation. See, they summarized from variety of field campaigns as well as lab studies. And what they observed that overall slope was -1. They were following the slope of -1. That is the slope of carboxylation. So why this so? So if you compare this with the study done over India, so this, for example, this is by Chakrabarti et al. Abhijit from IIT Kanpur. He did over Kanpur, and these are two different seasons, blue and red. You see, blue is foggy and red is non-foggy, and you see the slope, like with this slope. It is not -1, whatever I was showing in the previous slide. It was 0.74 versus 0.41. That was over Kanpur. And then we did over Ahmedabad. And what slope we got was 0.77. And that was just after monsoon, that means in September season. So we are getting 0.77, 0.74, 0.41. What these results suggest that oxygenated functional groups such as alcohol groups in addition to carboxylic group have contributed to the organic aerosol. However, it is yet to ascertain that how long it takes to get slope -1. or whether over India means slope ever goes to -1 or not. So that is yet to be done. Means still we need to do more studies to see whether means ultimately we are going to slope -1 or we have different kind of organic aerosol and it has different properties. So that we are still people are studying. Suppose if you know, so what? What is the implication of that? So implication is whomsoever is doing modeling, for them, they need to understand that with aging time scale, how fast do you go to slope -1? And from their perspective, why does this organic aerosol collapse to decomposition? Means what variety of organic aerosols are there? Why they are going towards carboxylic group? What is so special about that carboxylic group? And what are the details of fragmentation or functionalization reactions in the atmosphere that result in carboxylation, if they result in carboxylation? So to summarize, what we see that organic aerosols are dominant fraction of ambient aerosols. Speciation of organic components like PHA, sugar, diacids, isotopic composition of 13C, 14C, that offers greater insights in their sources and atmospheric processes. Then organic aerosol measurement with online instruments like HRTOF, AMS or PILS, LWCC, it provides better understanding of sources, characteristics and composition of organic aerosol. And then BRC is composed of, means whatever studies so far are there over India, what we infer that BRC is composed of many chromophores. Chromophores is absorbing component. That includes Hewlett and nitroorganics. They have variable optical properties. We have noticed that different time of the day the properties were different. And their absorbing property diminishes with atmospheric aging or oxidation during the photobleaching. But there is a lot to be understood about organic aerosol characteristics and their spatio-temporal variability over Indian region. And with this, I wish to thank you all. I hope you are all awake. You have not slept. And now there are